Yeah, okay. Welcome everyone to my session, and it will be, the talk of the session is Fruit of the Loom, and this will actually be about the fruits of the OpenJDK project that is named Loom, and hence the title. So this was actually like the first connotation that came to my mind when I initially decided that I'd like to talk about this project. But first, few words about me. So who am I? So I'm Arkadiusz Gasiński. I'm a Java and also a Kotlin developer and also a technical lead. And contrary to some beliefs, I don't wear my hat where I go to sleep. I do work at a company that is called GFT. This is a consulting company. This is our slogan. And we actually provide services for various industries, ranging from financial industry through the insurance industry, and we also work with the clients who, provide solutions, the so-called Industry 4.0 solutions. And if you happen to work in any of these industries and you have a tough problem to solve, or you want to create a solution that is tailored to your needs or to your customers' needs, then you basically come to us. Okay, yeah, so the talk will be about Project Loom, some, compiled information about this project. So it started in 2017, late 2017, so it's almost 2 years old now, just as my son, so I do hope that they will both age well. And, the goal of the project, at least according to the authors, is to make concurrency in Java simple again, or maybe to cite the project's proposal. Its mission is to make easier to write, debug, profile, and maintain concurrent applications that meet today's expectations, whatever they are. And, while the second part is something that I do agree with, I'm not sure that I agree with the first statement, that it will make concurrency in Java simple again, as concurrency is actually an inherently complex subject. But it will definitely make certain aspects of working with concurrency in Java easier. And so to achieve this goal, they propose to add some new construct to the Java platform, and I'll discuss this in a while. So you have some more information, like the project page. The project repo has been recently moved to GitHub, so this is a good news, because previously it was hosted on Mercurial repo. It was really hard to work with it. And last but not least, there are some early access builds already available, so you can try it yourself. So what's in store for today, actually, for the remaining part of the talk? I'll start with a short threads primer, because this actually is about adding new thread to the Java platform, so I think it's worth to spend some time considering what a thread actually is. Then I'll move to briefly discuss the Java thread limitations and what are its consequences for us developers. Then I'll cover the fruits of the project Loom, that is continuations and fibers. So these are the main two constructs that this project aims to bring to the platform. And then I'll cover the structured concurrency, like sort of a new kid on the block. This is a hot topic. Right now, it's explored by many different languages and platforms, ranging from C through Python, through Kotlin, and also it's explored in Java in Project Loom. Actually, the last part is, I think, the most exciting part. There's going to be a demo where I try to show you how to make Tomcat fiber friendly. And, I don't know whether we will have time for questions. So my recommendation is, if you have any questions, just raise your hand during the talk, and I'll try to answer if I can. So like I mentioned, because the talk will mostly revolve around the concept of a thread, let me maybe start by explaining what a thread really is. Maybe any of you have idea what a thread is? Okay, no, so Javadoc to the rescue. A thread is a thread. And you can have many of those in your application. So yeah, all clear now, right? I don't think so. So let's move on to some other sources. This is the threads definition in the concurrency Bible, which is Java concurrency in practice. And well, this is a bit better definition. So it basically says that it's like a control flow, and multiple such control flows can exist in your process, in your Java application, and that they share some process-wide resources, and they also do have some private data structures that are private to them, like program counter, which is an instruction pointer, or stack, or local variables. But actually, I do like the definition that's in the project Loom proposal the best, and this definition is that a thread is basically a sequence of computer instructions that are executed sequentially, so there is no concurrency in the thread itself, and actually some of these instructions that are executed may cause the whole computation to block, and if that's the case, the thread then should suspend, and it can be resumed later when the conditions due to which the thread blocked are no longer present. And obviously, the thread should behave as a good citizen, so while it waits, it should vacate our CPU. So I think that we have some understanding of like what a thread is, and let's try to generalize this definition even further. And I believe most of you are familiar with the term context switch. So it's actually a process of storing the state of the currently executing task and saving it somewhere to the side and resuming or restoring the state and resuming the execution of some other task that is ready to run. And actually, this process is performed by the entity that we usually call a scheduler. So essentially, we can think of a thread as a composition of two concerns, and these concerns are execution context as in context switch, and our scheduler, so the entity that assigns our context to the CPU. And we'll actually later learn that this execution context in Project Loom is implemented in form of the continuation. And now that we know what threads really are, let's think how we can implement them. So there are two ways nowadays to do that. You can implement this in the kernel level, so in the restricted area, and in the user level. And the difference is typically when you implement kernel level, these are the threads that are actually inside the kernel. So this is too low level. I won't be discussing this, but let's focus on the user level threads. So these are the threads that are basically supported and managed by the runtime system that we use, like our JVM. And they exist above the kernel, without or with little kernel support. And so these are the threads that you work with in your applications. And actually, in a specific implementation of these user mode threads, such threads must be mapped to the kernel threads, because this is the only way to actually get the access to the CPU. And basically, there are a few ways to do this. Many-to-one, one-to-one, many-to-many, and hybrid model. This is like entity relationship mappings that probably most of you are familiar with. So in this model, we basically have a set of threads that are living in the user space and that are mapped onto a single kernel level thread. And user thread scheduling is basically handled by the thread library rather than by the kernel or operating system. This is very fast and efficient, but it has the limitations that whenever any of these threads make a blocking system call, it blocks all other threads as well. So this is inefficient, and it also doesn't allow us to fully exploit the underlying hardware capabilities. Even if we had multiple CPUs, we have only one kernel thread, and we can't use more than one CPU or more than one core. Well, actually, this model was used by the first version of the threads in the early Solaris version of Java. It was called green threads. The second model is one-to-one model. It's a bit better. In this model, for every thread that lives in the user space, you have a corresponding thread in the kernel space, and this overcomes this disadvantage that whenever a blocking call is made, then your entire program is made. So in here, like if some thread makes blocking call, it only blocks one kernel thread, not the whole process. And but like obviously in this implementation, like all operations such as thread creation, context switching, and synchronization are slower due to the fact that they need some support from the operating system. Next model is many-to-many model, and in this model, like the limitation of the previous model, the one-to-one model, is actually that most operating systems places some limit, upper limit on the number of threads that you can have in your system, and actually this model aims to overcome this limitation, as you can have as many user-level threads as you want, and they're mapped onto a small pool of kernel threads, which is very efficient. And the last model is actually a hybrid combination of like one-to-one and many-to-many, so you can have many numbers of user-level threads mapped onto some pool of kernel threads, and actually you can also have some kernel threads that support only some threads, on some dedicated threads that lives in the user space. And yeah, so like these are threading basics, and what are the consequences of these models? Well, basically, Java, most of the modern versions of Java at least, employ the one-to-one model. And we've learned that in that model, thread creation and context switching are slow because we need to ask operating system for some support. And obviously, there is an upper limit on the number of threads that you can create. So the next point is actually a direct consequence of that, is that your domain unit of concurrency cannot match your software unit of concurrency. So if you want to employ a model thread per request for, say, serving your incoming HTTP traffic, you cannot do this easily with threads. At least you cannot easily predict the system capacity using that approach. And obviously, if you create a large number of threads in your Java application, this will place a huge load on the kernel scheduler. So your CPU, instead of running your application, will be running kernel, doing all of these context switches. And obviously, when your task block, it also blocks an underlying kernel threads. So if your workload is that you have many tasks that frequently block, you won't be able to utilize your resources efficiently. How does it look in practice? So this is a classical example of a contended lock in Java. We have our critical section, we have our monitor owner, and we have our wait set. And well, this is actually typical in many Java applications. And it illustrates the problem that basically when your task cannot proceed, it not only blocks the task, but it also blocks the worker that is doing the task. So how do we, what's the answer? How do you overcome these limitations nowadays? So obviously async is the answer, or reactive is the answer. But it actually comes with the price, and actually to fully take advantage of asynchronous or reactive programming style, you actually need to adjust each and every layer of your application. And of course, you can do it gradually, but obviously there is a vast amount of work involved in that. And yeah, obviously, I mean, learning the new style of programming, it also brings some overhead. It's much easier to work with asynchronous code comparing to the familiar sequential blocking code. So yeah, this is and obviously this brings some maintenance cost as well. And also, if you want to have or expose an asynchronous API, then you need to learn you force your clients to actually refactor their code as well. And you then need to support two APIs, one for synchronous, one for asynchronous processing. So there's no option to have a single API to rule them all. And yeah, if you've ever tried debugging async code, you know how it feels. So yeah, I won't be talking about this much. And actually, Project Loom aims to be the real answer to these limitations that we've just discussed. At least, yeah, according to the authors. And like the slogan for the project is code like sync, run like async. I'll try to explain that in a moment. So continuations, I'll now discuss the constructs that this project aims to bring to the platform. So continuations are actually a low-level construct, and we as developers, and I consider myself a developer, are apparently not supposed to work with them, so I won't spend much time talking about them, but they're basically a fundamental building blocks for fibers, which are the new user-level lightweight threads. And you know, as we already know, that thread is a composition of two concerns: the context and the scheduler. And this context in Project Loom is implemented in the form of continuation. And well, sometimes we call continuation like the rest or the future of the program execution. So this is actually a construct that allows us to capture execution context or just capture execution of our computation. And we provide this computation in a form of familiar runnable interface. And this runnable interface may actually contain instructions that cause our computation to block. And when that happens, we say that computation should yield, so that it should pause the execution. And once the conditions due to which the computation was blocked are no longer present, the computation may continue. This is the API, so like we have two constructors. Basically, well, there's this continuation scope argument. I'll discuss it in a moment. And the other important argument is the runnable, so our computation that we want to be running within the continuation. And there are some methods like run that actually starts the execution and is done that basically says whether our computation is finished or not. And by finished, I mean that it went from the beginning to the end, and that it's not suspended. Like when the computation is paused is done, we'll actually return false. So this is a basic example. I don't think I'll be covering that in much detail, as I want to do the demo really. So this is the continuation scope. This was the first argument that we do pass when we create our continuation, and this is the argument that allows us to nest and compose continuations. And actually, when you create continuations, you can create a continuation within a continuation. And when you want to yield a continuation, maybe I'll go back to that slide for a while, because an important method that you see here is actually the yield method that pauses the computation. But this is a static method, so it's not like that you have a reference to your continuation and that you can call yield on that reference. You actually call yield giving the scope that you want to pause. So you don't yield continuation directly. Every continuation runs in some scope, and when you want your continuation to pause, you actually yield the given scope, and whichever continuation is running in that scope will be paused. Yeah, so this is about nesting, but like I said, I want to do the demo, so I'll skip that. Yeah, another example, you can actually implement a Fibonacci sequence using continuations. Okay, and if you want to find out the low-level details of how the continuations is implemented, under the hood, what happens when you want to pause your continuation and what happens when you want to resume your continuation, I'll just send you to this talk by Ron Pressler, which is the project's technical lead. It's a great talk and covers all these details. I won't do it better. Current limitations. There are a few limitations, and these limitations are essentially about when your continuation can actually pause and when it cannot. So the first limitation is when the kernel thread on which continuation is mounted. So actually, you always run continuation in some thread, some Java thread. And if that thread happened to be holding a native monitor, so then you actually cannot yield this continuation, and this is because the thread is actually an owner of that monitor. And if you'd like to pass that continuation, what do you do with the lock held by the given thread, right? This thread should be maybe running some other computations, but it owns some lock, so you probably should pass the ownership of this this monitor to, I don't know, continuation. But well, this is implemented deeply into inside the VM, and it requires a significant amount of work to actually implement. But this is something that can be done, and the authors claim that they will actually do this eventually. But there is also another limitation. Okay, I don't know why this skips, but actually this other limitation is when there is a native stack on the continuations. There is a native stack on the continuations stack, so this may happen when you actually run your computation inside the continuation, and in that computation you do some JNI call, some native call, and then your native call calls back into Java, and you try to yield your computation. Then it is impossible to actually yield this computation. And by default, continuations throw an exception, but fibers override this behavior. So this is just an example, like what happens when you try to yield the continuation when that holds a lock. So yeah, fibers. Some useful information. So this is like this new user-level thread that is added to the platform. And well, it is the user mode thread. It employs the many-to-many mappings, so you can have as many as you want or as many as your actually system, because obviously there's going to be some upper limit. It's not the same as with plain old Java threads, but there is obviously some limit. But this limit you will count it with millions rather than thousands, as with typical threads. And its footprint is really low, so the metadata is like around a few hundred bytes, and stack is actually pay as you go. So like whatever is currently inside your continuation, this is the cost of your stack. And you actually use any executor implementation as its scheduler. If you don't customize the scheduler, the fork join pool will be used. And it is all implemented in the VM compared to, contrary to continuations, which are mostly implemented in the thread is implemented in the Java standard library, continuations in the VM. And yeah, they do still rely on the plain old Java thread for the CPU access. So how do we run our tasks in fibers? We actually first need something that we call fiber scope, and this is like a container for our fibers that are created with it, and it actually manages and tracks all the fibers that were created with that scope. So yeah, you have like a container. You have some options to open that container. You can define that that container will live for just some time, and after this time, expires, the threads that are still, the fibers that are still running in that scope will be canceled automatically. So yeah, so that's how you you first need to get this fiber scope, this container for scope, in order to be able to execute something in fiber. And actually, once you have this container, this fiber scope, you actually use schedule methods that are, defined in the class to execute your code with fibers, and you pass your computation in forms of either runnable or callable. And you can optionally customize the executor used. So, like once you have your fiber, you cannot actually do do much with it. So, like you can, the join method is for waiting for fiber's result. And you can you can also like convert it to completable future to adjust it. If you have an API that employs completable future, you can easily convert it to that representation. You can wait till it terminates and just check whether it's alive or cancel it. And what about support for fibers in the core libraries? So like, many JDK libraries have already been retrofitted to work with fibers or to be aware of them. And these include, Java.io, Java.NIO, all classes from the Java util concurrent package, and the primitives that we see here, such as thread sleep or thread join. And this stack trace actually is from the application that we'll be using for the demo. It shows what happens when you try to park a fiber. So in this case, we have a call to completable future get, which is a blocking call, and this in turn causes our fiber to be parked. And when we park a fiber, we basically yield a continuation on top of which the fiber is built. And when we want to unpark a fiber, it was a bit harder to catch a stack trace. You basically schedule fibers continuation again, because fibers continuations implements is runnable, so you can just make it run again. So it's like resuming continuations execution. So these are some examples that shows what happens when that when you actually call thread sleep method, and if this method is executed in the context of the fiber, it's not the underlying kernel thread that will be blocked, but it is the fiber that will be blocked, and this underlying kernel thread can be used to do some other useful work. The same goes for Java util concurrent lock. So for IO and NIO, we'll try to do that during the demo. And so the last key item of the theoretical part is something that we call structured concurrency. And like I've mentioned, this is like a hot topic nowadays. It's been explored by many different languages and platforms currently. And what it is about, so like to put it in layman's terms, it's basically when you have one function foo that calls some other function bar. So like, if bar creates or starts some threads, you want all these threads to be gone by the time bar returns. This is all what it is about. And actually, like, I bet you've heard about the term dependency inversion. So we often use the term Hollywood principle to define it. So it says, don't call us, we'll call you. And if I were to define a similar slogan for the structured concurrency and use some US city for that, I would call it a Las Vegas principle. That is, what happens in Vegas stays in Vegas. So basically, it's about like whatever, like once you return from Vegas, you don't want these like activities or like whatever you done while you were there to haunt you for the rest of your life. And the same way, you don't want the functions that are already returned to be messing with your application. So this is some other example, like why it's important. So we open some file and want to print the content of that file, and to do that we call some method. But let's assume that we don't know that this this method actually prints the content of the file in a separate thread. So like as soon as we return from the print file content, we are like almost confident that like the file content was printed, but that's not the case, because it's running in a separate thread. As soon as it starts actually printing the content, we get an exception. So this is the structured concurrency is actually to prevent things like this. And how structured concurrency is implemented in Project Loom. So we already saw this. Actually, the main construct that allows us to achieve structured concurrency in Project Loom is this fiber scope, so this container for threads, right? And this it implements the auto-closable interface, so we can use it in the try with resources statement, and we can create and open a scope and schedule as many tasks as we want to be executed with that context. And we won't exit that scope until all the tasks that were scheduled in that scope are terminated. So what do we do before Loom is released? Here are the instructions. Please follow them sequentially. And yeah, time for the demo. Hopefully, I'll stand the jump. Okay. So this, this is actually about making Tomcat fiber friendly. Okay, that's actually not that one, so let me maybe close that if I can. And yeah, so how to actually start with this? Maybe some code would be good. Where are all these? Yeah, that's it. Okay, so actually this is like, the setup is that like we have 3 different, well, microservices. Yes. Or maybe I'll turn on the presentation mode if I, okay, and just 1 second. Sorry for that. So in the meantime, like the setup is that we have like 3 services in our system, and we actually want to generate some load onto one service, and this service in turn uses a discovery service to discover the other upstream service, and calls that upstream service, and that upstream service responds within like from like 0 to 1 seconds. And we want to run this either in threads or in fibers and see whether there's any difference at all. So yeah, just 1 sec. Okay, maybe any tips how to turn on the presentation mode? Okay, thanks. Okay, yeah, that doesn't work as expected. I'm sorry for that delay. Okay, and I lost my... Yeah, so that's a bit annoying. Like it is completely gone. Let me close that. Okay, here we are. And view and appearance and nothing happens. Okay, yeah. So we have an instance, like actually these are all Spring Boot services running on top of a Tomcat container. So I wanted to customize them so that like to provide my own executor implementation that would use fibers under the hood. So this is what I actually had to do. I call it a fiber thread executor. So when you create it, you can actually configure it whether you want this instance to run with fibers or with threads, and that's how the execute method is implemented. So essentially, what happens here, we have some fiber scope that is like the global scope for our connector actually, and we use that scope to schedule processing of incoming HTTP traffic. And all the requests will be executed within the fiber if we configure this class that way, and if we want our executor to execute tasks within the context of a regular thread, we basically just submit the tasks to the scheduler directly and not to the fiber scope. And so the initial attempt, and to do that I'll have to exit the presentation mode for a while. And actually I do have a custom Tomcat version. Let's start with the no modifications to the Tomcat. So I'm gonna comment this for a while, and actually let me show the terminal. Okay, it disappeared. Oh no, it's here. Or it is. Yeah. Okay, for some reason I cannot move the terminal to. What about terminal from PROIDEA? Okay, yeah, there it is. Sorry, yeah, that should work as well. So actually, I'm gonna. I had the instances of this services running. I'm gonna shut them down. And okay, that doesn't work well. Yeah, I do have more terminal tabs open than Chrome tabs open. Too bad. Actually, let me maybe close all these and let me quickly rebuild these services. So actually, I use Gradle to do that, and this works with the latest JDK, the Fiber JDK, and that would be the so we'll try to see how it works when we run on an unmodified version of the Tomcat servlet container, and I'm gonna run this service. Maybe first open another one, and we'll run the discovery service using so I'm starting my discovery service. Next, I'm gonna start the service, upstream service that we'll be calling, which we call echo service. And last but not least, I'm gonna start the workshop service, which is the service that we'll load test. Okay, and I actually do have a script which is called attack. I'm not sure if you can see it, but basically, like the service that we will be load testing contains the Tomcat connector. The first, basically processes all incoming traffic in the context of Fiber. The second in the context of a plain old Java threads. There are some like ways to configure it, and let's start with let's see how fibers work on unmodified version of the Tomcat, and I'll actually have to modify this a bit because the rate is too high. We don't want 1,000 requests per second because this service actually employs 2 threads to process incoming traffic. This was easier to actually show. So how we call it, and we should actually get some requests. We can see them, and we should see some of them here as well. So that should actually work. And it once it finishes, it generates a nice graph that we can see how it all looks. I'll try to show that graph in a moment. Okay, and yeah, let me actually see if that already finished. Not yet. So like we see, we have like 2 threads. All the requests are processed in the context of the fibers, and it's only like 10 requests per second, so not that much of a load. And the script should actually end within like 10 seconds, but it's still running, and it's because like we only have 2 threads, and there are like the timeouts. Or basically there is a queue, and all these requests are queued, and the processing is done slowly one by one. So not much of a gain from the fibers when we use the default Tomcat implementation. So let me now try to actually switch to this new implementation. And for that, I'll have to, I'm going to cancel that. And as you can see, like there is a total of like almost 400 requests sent, and the rate was like 6 requests per second. So let's rebuild the process. Okay, that's done. Let's run it again. So right now it uses the customized version of Tomcat that actually executes, that is fiber friendly. So let's start with the initial load of 10 requests per second. And let us see how, like if there is any difference. It should end, well, actually, I guess that's my bad. I'm gonna edit it again because it runs for 120 seconds and we don't want to wait that long. So, yeah. And let's run it again. So we see that there is the load there, and hopefully it finishes. Yeah, it finished within 10 seconds. So as it should, like we see the 100% success ratio, but that was only, like we still have 2 threads, but that was only 10 requests per second, so actually not that much. So let's see how this actually handles more than 10 requests per second. And let's try maybe, I don't know, 100 requests. That should actually work. Okay. Yeah, we do have 100 requests, and let's attack the service. So we see that what's happening here? We shouldn't be getting the response here. Okay, but it actually finished the execution. And yeah, I must have made some error in there, so I don't know if there is any special character. Did I did something wrong with it? So rate is 10. Okay, I think, yeah, working with Vim, I should have listened on the previous talk. Okay, yeah, that should be fine. Let's try again. Okay, yeah, let me maybe open this in IDEA. And maybe removed all the modifications. And yeah, the rate is 100, so let's run it again. Okay, it looks better. We see the load. And let's see, the timeout is 10 seconds, so it should actually finish soon. The timeout that we do see in here, okay, I've changed the timeout, I didn't change the duration. So again, my bad. I want it to be like this, but we can actually console like this. And we can see that we've been running this with the rate of 100 requests per second. We only have 2 underlying kernel threads. And the success ratio is like 100%. And we've handled all the incoming traffic. So let's maybe try increasing the rate from 10 to say 1,000. Let's see how it performs with thousands requests per second, whether there is any difference. I'm gonna maybe increase that a bit again. So yeah, we've generated 10,000 requests in total, all of them completed successfully. And if we were to look at the graph that was generated from this processing, we can actually see that, like, this is how it looks. It got much denser because we had like much more requests that we processed. We only have 2 underlying kernel threads, and we've handled all these requests like within up to 1 second. And the 1 second is actually what takes to get the response from the upstream service, right? So this all looks really well, and maybe I'll try again running the same with threads actually to see the difference. Well, to actually see if there is any difference, and to run the same in threads, I actually just need to change here to threads. So I'm only sending 10 requests per second inside in case of threads, and we'll see how the system behaves in a moment. So I'm gonna close that one. This is like the old graph for threads. I'll refresh it. Yeah, okay. So this is how it. Actually, nothing is printed in here. I'll have to show you the data in the HTML file itself, but most of this data is probably not a number because the server actually failed to respond within the 10 seconds, because this is the read timeout that is set in the tool that we use to load test the service. And as you can see, only like 58 requests responded with 200 code. So it's about 58% success ratio, and this is only 10 requests per second, right? And we tested the same endpoint that actually does the same job, but does the processing in the context of the fiber. And we could, it handled 1,000 requests per second without any issues. And because, what's happening there is basically our service or our fiber call an upstream service and wait for its response. And if we were actually to see how this looks in the visual VM, we would actually see that, well, this is from the old execution, but we would basically see that actually our fiber carrier thread is yellow all the time. And that's because this thread basically waits. So we have our 2 fiber threads. Let me generate some more fiber load. Okay, so it's runnable for a while, but it's actually maybe not waiting, but it's parked most of the time, right? So it does some job from time to time to handle the incoming traffic of 1,000 requests per second, but it's actually parked most of the time because it doesn't have to do anything. And actually, I didn't mention that, but fibers are good for the IO-bound applications, which are the applications that do a lot of IO operations, and they are not that good fit for the CPU-bound applications. So if you have, an application that uses CPU a lot and doesn't yield or pause frequently, then fiber may not be the best match for this type of workloads, right? So essentially, the problems that fibers aims to solve are mostly concerned with the IO-bound applications. Okay, so I believe we are done with the load. Again, we have a 100% success rate, and yeah, it didn't work with the 10 requests per second with plain old Java threads. So yeah, well, I do keep my fingers crossed for this project to be delivered as soon as possible. And yeah, actually, that's it from my side. Thank you all very much. And by the way, I do have some gadgets from my company, so if anyone is interested, you can just come here and grab some if you want. Thank you.
Thank you very much. That was